Thank you very much. And thank you, Bill, of course, for providing us with such a nice occasion to hear a wonderful amount of nice mathematics. You know, I always remember the mini course Bill gave in Lens a few years ago. I think it was one of the best mini courses I ever heard. And well, in the north of France, we remember your mini course and talk about it from time to time. So that's really something. So what I will talk to you about today, well, is not about Banach spaces of analytic functions, but I hope that in the end, if you're working in Banach spaces of analytic functions, you will get ideas about what you could do with that. So what I'm going to talk about is joint work with Étienne Matheron, who is from Lens, and Quentin Menet, who is now in Belgium. And it is about typical properties of operators. So it's a rather general framework, so I'll begin with that, since you may not be familiar at all with the topic. So what do we mean by a typical property? So the setting is the following. So we'll start from a Polish space. So what is a Polish space? So it is a topological space which is completely metrizable. So it means that you can define the topology thanks to a metric which turns it into a complete space and separable. Right, so as you know, when you want to define completeness, you can only define it in the metric setting. Polish spaces, it's the analog, but in the topological setting. And it's, well, the good setting to do Baire category arguments and many things. So typical examples are, of course, complete separable metric spaces. That's basic. But also, let's say, G delta subsets of complete separable metric spaces. So, for instance, if you take for E the open interval 0, 1, and go with the topology of R, induced by that of R, then it's going to be Polish. Right. So that's the setting. And now, if we are in such a Polish space, so if we consider a property, let me call it capital P, of elements of E, we're going to say that it's typical if, when we consider the set of elements satisfying it, then it contains a dense G delta set. So that is, so I should have defined it here already, a countable intersection of dense open subsets. Right. So what it means is that the set of elements having property P is large in the Baire category sense, right? So it means so I'll also employ from time to time for that the word comeager. So comeager means containing a dense G delta set in the Polish space. And a sentence which I will use often which the audience usually finds a bit disturbing, so I'll spend two minutes on it, is I'll often say that a typical element of E has property P. This means exactly the same thing. When I'm going to say that an operator, a typical operator has such and such a property, I will mean that the set of operators, let's say having this property, is comeager, that is large in the Baire category sense, right? So just one quick example to get used to the terminology. So you agree that a typical real number is irrational with the classical topology of R? Right, so that's exactly the way of saying that if I consider the set of irrational numbers, well, it is a dense G delta set in this case. And not so trivial example, but not difficult either, is, for instance, suppose that I consider for E the set of all Borel probability measure on the segment 0, 1, and I endow it with the Wickstar topology of measure, then a typical measure in this space is both continuous, so which means it has no atoms, it puts no weight on any singleton, and singular with respect to Lebesgue measure. So, I mean, this is, if you have never seen it, this is not just half a line, but you show that the set of measures satisfying that is a dense G delta set, and the set of measures satisfying that is a dense G delta set as well. And you can rephrase it as a bit weaker way, but as saying that a typical measure has these two properties, right? Okay, so that's the general setting. And something important which I implicitly used here, but which I will write down so as to have it clear, is that by the Baire category theorem, if a typical element of E has P1 and a typical element of E has P2, then a typical element has both P1 and P2, right? So that's straightforward, but it's quite useful when you get to study typical properties in more depth. Okay, so that's that. So now, what's going to be our main interest? So we'll consider the following setting. So we'll consider the Banach space of LP summable sequences. So for P between 1 and infinity, so it will have its usual canonical basis. I write it here for when I need it. And then the idea is to look for typical properties of elements of B of E, X, that is, bounded operators on X. So, when you want to do something like this, well, you need to find a topology which will turn your space into something Polish. And you very quickly see two things. The first one is that you will have to restrict somehow your space. So let's say to operators which are contractions, norm less than 1, because else you get very little chance of doing something. And the second thing is that the most obvious topology you might think of, which is a norm topology, won't ever give you something separable. So you have to do something different. So So there will be 4 topologies, so I'll try to be quick so as not to bother you too much. So there will be the strong operator topology, so that's the topology of pointwise convergence on the space. So you say, so for every x in your space, you're asking that you have convergence in the norm, right? So you have the weak operator topology. So here you're requiring that you converge weakly to Tx. And so these two are very well known to the operator theory community. And then there will be two more, which are perhaps a bit more exotic, but not much more difficult. So here you require the pointwise convergence of the adjoints, and here you require both pointwise convergence in norm of the operator and pointwise convergence in norm. So I mean, I try to be quick, right? But this sounds nicer, right? So here. And what we would like to have is that these topologies on B1 of X would be Polish. So actually the situation here is rather nice. So this is Polish for every P bigger than 1. And in the other cases, for reasons which, well, may be essentially obvious from the definitions, but you see that the case L1 is going to be problematic. So here we exclude the case where x is equal to 1. So I don't want to spend too much time on these topologies, but perhaps a picture will help you get the feeling of it if you're seeing this for the first time. So imagine that we have a contraction on one of these LP spaces. So if I want, I can formally write it as a big matrix, right, with respect to my canonical basis. And then I'm trying to understand what it means to be close, for an operator T to be close to T0 for one of these topologies. So for the WOT topology, it means that for some epsilon and for some n here, the two matrices here for T and T0 are going to be close. For SOT, it means that these columns are going to be close. And for the other two topologies, right, SOT with the star up, the first n lines will have got to be epsilon close. And for SOT star, you will have to require it both for lines and for columns. No, that's SOT star down, and here it's SOT star up. Okay? Right, so this matrix, I hope, helps to visualize a bit what's happening. Okay, and so now the goal is the following. So, okay, I'll write it here. So it's a very general goal as it stands. So we take a topology, so one of these four ones, and then very generally, so find typical properties, so hopefully interesting ones, right, of an operator T for a contraction on X with respect to the topology tau. Of course, for p equals 1, it's only for the SOT topology. So actually, when with Étienne and Quentin we started this business, there was a motivation for that, which was trying to understand better the invariant subspace problem, actually, because that's once you have started thinking like that, there is a very natural question. Is it true, for instance, that a typical T for one of this topology has a non-trivial invariant closed subspace, or whatever, but in this direction. So that's a way of trying to understand whether it's hard or not. So it's hard, that's no news. And trying to understand also the difference between the different property between the spaces and so on. So actually, I'll try to summarize on this blackboard what we know and what we don't know, and then I'll move to results. Okay, so I'll put here the topology. So SOT, SOT star, and SOT star. And then I'll put here the spaces. So, so here below we'll put typical property of contractions on X. So it should be no surprise that there should be at least 3 different cases. You have L1, you have L2, and then you have the other ones. And perhaps these later boxes we should subdivide afterwards. So I did that badly because it's for L2 that we know the things best, so I should have put a bigger box. So I'll try to put it right. We'll see, okay. Sorry. Okay, so actually the study of typical properties in this setting was begun by Tanja Eisner. So it was she who proved the first results in this direction. So what she proved here in this box for the WOT topology is that, well, a typical T in B1 of L2 is unitary. And she gave some more details about what's happening, so that's Tanja Eisner here. So that's a rather well understood situation. And then together with Tamas Matrai, she also could say several things concerning typical properties of SOT contractions on L2. So they proved that a typical T is unitarily similar to the backward shift of infinite multiplicity on the direct sum of countably many copy on L2. So this has the following consequences, that whenever lambda is smaller than 1, then the range of T minus lambda is closed, and the kernel of T minus lambda, so the associated eigenspace, has infinite dimension. Right, so that's a very strong result, which you can say about a typical contraction on L1. And so in both cases, you see that the existence of invariant subspace for a typical contraction is okay here because you have a unitary operator, and here because, well, for so many reasons that, well, you do have an eigenvalue, and that's it, right? And so that's a pretty clear picture here. And then we started on that and tried to understand the boxes. And we were especially interested in this box in view of Fried's counterexamples on L1, examples of operator without non-trivial invariant subspaces. So what did we do first? So L1, so right, here topologies are not Polish, so there is this box to fill. And the result in this box is disappointing, right? Because we proved that a typical T on L1 is such that T star is an isometry, so on L infinity, and, well, exactly the same. For lambda smaller than 1, the range of T minus lambda is closed, and the kernel of T minus lambda has infinite dimension. Right, so that's a disappointing result because as far as invariant subspaces are concerned, here basically you don't make any difference between L1 and L2, which is a bit strange, right? But that's the way it is. Well, okay, for these two boxes, so I think you agree that when you look at the definition of SOT and ISTOT star, just going to the adjoint. So I'm not going to rewrite everything here, but this you can basically copy with the proper modification of the joints in this box. And so that's okay. Obviously, a typical T has a non-trivial invariant subspace, so that's okay. And here, the answer is yes, again, but for reasons which are not completely as trivial as here. So what you can prove here is that for the SOT star topology, a typical contraction on L2 is such that it has maximal spectrum. So its spectrum is the closed unit disk. And then you have a well-known theorem by Braun, Chevreau, and Percy, which tells you that if you have a contraction on the complex Hilbert space whose norm is less than 1 and whose spectrum contains the unit circle, then T has a non-trivial invariant subspace. Right. So here, if we add this ingredient here, the existence of an, why do I write ISP? Non-trivial invariant subspace is okay, right? But this is quite a non-trivial result, right? So we use it kind of as a black box, but there's, well, more mathematics in that box than in the other ones. And then okay, we get some kind of picture of what's happening in these two cases, and then we have the LP case, which we try to investigate next, and this is what I'm going to talk to you about now. So I don't know. No, that's not it. Wait. Okay. So before I start with the LP results, I would like to point out something, well, which is pretty obvious on this board, but important to remark. That is, well, if we have two different topologies, right, here we're on B1 of X, but it is a general comment I'm making now. Then you have no link between typical properties for one topology and for the other topology, right? for instance, if you, right, let's say you take WOT and you take SOT, right, if you have something which is tau open, then it's going to be tau prime open. And if you have something which is tau prime dense, then it's going to be tau dense. But, well, two ways, and so no way you can build a dense G delta set starting from one and going to the other. And that's why the typical properties may be widely different when you change topologies. But, okay, once you have remarked that, there comes a natural question. Well, are there cases where typical properties for tau and for tau prime may be the same after all? So it's not what happens here. But once we have worked out the Hilbertian case, well, I mean, it's something we realized with Étienne and Quentin, that actually when you're trying to look for typical properties, the easiest box is this one, and it becomes harder when you go there. That's what happens. And, well, it turns out that it is indeed the case, and sorry. This property has a name. So let's use the name. So if we have two different topologies, on, let's say, an abstract set M, here I'm not asking anything Polish or whatever, we say that tau are similar. That's probably not the best name for it, but that's what was in the literature, if they have the same dense sets. So, okay, here, we're not interested only in density, right? We're interested in comeagerness. But there is a very nice fact that if two topologies are similar, then they have the same comeager sets. So that's a few lines proof. It's not something difficult, but well, at least it reduces a bit the complexity of the matter, that you only have to care about density. And well, just a very quick example, so that you get a feeling of similar topologies. Okay, if you're on R, right, that's your set M. So if you take for tau the usual topology, and for tau prime, the topology which is generated by half open intervals. Right, you take that. Then I'm claiming that these two topologies are similar. Right? Okay, same dense sets, I think you agree. But they're widely different, right? We know the topology of R, but if we endor R with these topologies, then it's going to be a set, it's going to be a space of dimension 0, right? Every point has a basis of closed and open sets, so it's totally disconnected, so it's looking very weird from our point of view. So it's not saying at all that the topologies are the same, but for typicality purposes, they will be the same, right? Okay, so now I think I can state two theorems. So the first one tells you the following. So if P is larger than 2, so that's an assumption, we don't know what happened for P smaller than 2, the topologies SOT and SOT star are similar on the set of contractions on LP. So that was kind of unexpected for us, but this is indeed what happens, so wildly different from the case P equals 2. And it has a corollary, which is that for P bigger than 2, a typical contraction on LP has no eigenvalue. Right. So I don't have time to give you the proof, but the idea is the following. If you work here with the SOT star topology, it's not very difficult to show that a typical T is such that the spectrum is the closed unit disk, again, so this is not specifically Hilbertian, and T has no eigenvalue. What you're bothered with in this situation is the fact that the set of operator without eigenvalue is going to be G delta, and that's much easier with the SOT star topology. And so now, what theorem A is telling you is that this goes over here. So typical T has no eigenvalue. Right. So the proof of this theorem is a bit of work. If I have 2 minutes in the end, I'll tell you about it. So at least it rules out the possibility that a typical T on LP has an invariant subspace for a trivial reason. But we don't know, actually, whether a typical T on LP has a non-trivial invariant subspace or not. That's wide open. Okay, and then well, once you've got this theorem, then the next question, one of the next question is, okay, and why P bigger than 2, and what happens when P is smaller than 2? And so we tried rather hard with Étienne and Quentin to see whether for P bigger than 1 we may have eigenvalues or not. And we failed, but we came across the following curious result. So that's the kind of theorem which, well, it's pretty useless, but it's nice in the same. So I try to explain. So what does it say? So it says the following. So suppose that P equals 3, right? So that's a bad beginning. And suppose that your LP space is real, even worse. And then all topologies WOT, SOT, SOT star, and SOT star up are similar on B1 of L3, right? Okay, so it tells you that in this case, all topologies are similar, and so you have the same typical properties. And the interest of this thing is that it goes over to the conjugate exponent, right? Because with WOT you can... So this is less than 2, and that's the only result we have in the case where P is smaller than 1. So I say this is a pretty useless result because well, the assumptions are rather restrictive, and moreover, here we assume that LP is real. So we cannot deduce anything in the way of T has no eigenvalue or whatever. We would need the space to be complex in order to be doing that, and we can't. So that's how matters stand for the time being. So I still have 4 minutes, right? So I'll try to give you in these 4 minutes just an idea of the tools which we're using. So it will be pretty sketchy, but
Are you saying it doesn't work for P not equal to 3 or 3 halves? Your proof doesn't work for P not 3?
Sorry.
It's very specific to 3 is what you're saying?
Yeah. I mean, that's something pretty tough in this theorem. We need it real because we'll be working with norming vectors, and we need them isolated in the construction. And when the space is complex, when you have a norming vector for the topology, you just rotate it, and it's not isolated at all. So that's a silly reason, but that's precisely the reason for real. And P equals 3, it's because we have to do some computations on quantities of this kind. You know, working with LP norm is tough. And we tried very hard with P equal 5 or whatever, to try to push it a bit further. But I mean, at least the only thing we can do is P equals 3. So that's, but it's a natural question. We were not happy with it either. Okay. So, what are the tools? So these are theorems which you can prove in different ways. I mean, there are several points of view. But the one which I would like just to advertise here is continuity point. Right. So we have 2 topologies. So topologies, that's what I wanted to write. Let's not be too general. So one of these 4 topologies. And, we can consider the identity map as going from the set of contractions on X endowed with one of these topologies to B1 of X endowed with the other topologies. And we denote by C of tau prime the set of points of continuity. I'll write it tau prime. For this map. Right. So saying it's a point of continuity means that if you're tau close to the point, that in fact you're going to be tau prime close to the point. And you have a fact, something which you can prove, in that in this setting, this map is of Baire class 1, which means that whenever you take a set here, which is tau prime open, then it is, so if I want to write down the continuity in a way you recognize, is tau f sigma, right? Countable union of closed sets. And this is interesting because under this assumption, C of tau prime is a tau dense G delta set. So this tells you that a typical element, a tau typical element of B1 of X is going to belong to this set. So then now you have a road. You consider, let's say, continuity points from SOT to SOT star, and you try to identify them, see what they're like, etc. And for instance, I mean, in the Hilbertian case, you can exactly identify that and say the set of co-isometries, for instance. And I cannot go into details, my time is over, but that's how we work to investigate typical properties, and there is a reformulation of similarity also in terms of points of continuity, and so that's how it goes. Okay, thank you very much for your attention.
Thank you very much for your lecture. Are there questions, remarks? So for the theorem B,
Yeah.
so P is equal to 3, is it real? Because you're trying to use calculus to do it, and because you have to do them, you're actually working.
Yeah, this is exactly what I was starting to explain, that you know, in the proof of this theorem A, we want to, actually, once we've gone through all this continuity point stuff, etc., what it boils down is constructing operator, so contraction, whose norming vectors span a dense subspace of the space. That's what it's like. And what we want to do is, well, we build an operator with the first norming vector, and then we want to complete it in a way so as to build another norming vector without modifying it too much, etc. And there are computations in that involving quantities of this kind, and working with LP norms. So here, you know, you can expand, you can compute, you can, but even for odd exponents, integer odd exponents, we don't know. So
for like 5, it just gets to be too much?
It's even not that it is too much, it's just that it's not working.
Oh.
It's even worse, actually.
Oh.
Yeah, at least we didn't manage to make it work. So it's kind of a glimpse of what could be true, but for the moment it's pretty unsatisfactory the way I see it. Yes, John?
So you have results for L1 and L2. Have you heard about some sort of interpolation? How is an interpolation is overly restricted and just looking at boundedness? It really should be.
Yeah. Interpolation is something we thought about, yes, and we tried, but we couldn't make it work. I mean, we can talk about it afterwards if you have a better idea, but if finding contractions on LP spaces from interpolation between L1 and L2 from the Baire category point of view, I mean, we couldn't go through that way, but maybe, I don't know. LP is rather mysterious. That's, yeah.
So for the case P equals 3, you say that you could go to the dual index.
Yeah.
Why can't you do that here?
Because here, you know, I jump from this box to this box, but that's all I can do. I mean, you cannot say that a property is typical for SOT if it is typical for SOT star bottom. I mean, it's for a silly reason. I mean, you know, what this theorem is telling you is that basically, you know, I didn't write it that way, but what it tells you is that if you know something here, then you're going to know something here, right? So perhaps I should have written it like WOT and SOT star down are similar. So you can go like that. And so, of course, with SOT and SOT star, then since you know that you have the columns as well, then it goes through. But we don't know how to go from WOT to SOT. That's the big open thing, actually. So that's it.
There are no other questions, so thanks, Sophie, again.
Thank you.